This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers around a fascinating interactive physics simulation, component of a vector or sine and cosine components JavaScript HTML5 applet simulation model. It's part of a larger open educational resources project, and it's designed to make learning physics more engaging.
Precisely. Interactive simulations offer a powerful way to visualize complex concepts, allowing students to actively participate in the learning process rather than passively absorbing information.
And this particular model focuses on vector components, a notoriously tricky topic for many students. How does the simulation address this challenge?
It uses a 3D visualization, which is key. Many students struggle to conceptualize vectors in 3 dimensions. The simulation allows them to manipulate the vector and see how its components change in real time.
So it's not just about seeing the answer, but understanding the process. That's a significant advantage over traditional methods. Let's delve into the specific features of the simulation. You mentioned the 3D visualization. What other interactive elements are included?
The applet incorporates sliders to adjust the vector's magnitude and direction. This allows students to experiment with different values and observe the resulting changes in the components. There are also play, pause, and reset buttons for controlling the simulation's flow. And, importantly, it's embeddable in web pages, making it easily accessible.
The ease of embedding is crucial for integration into online learning platforms. It's a practical feature that enhances usability. What about the educational goals? What are students expected to learn from using this tool? The simulation is part of a broader Open Educational Resources (OER) initiative. Can you explain the significance of OER in the context of physics education?
OER promotes accessibility and affordability. These resources are freely available, removing financial barriers to education. This is particularly important in physics, where access to sophisticated equipment can be limited. The open source nature also fosters collaboration and allows educators to adapt and improve the materials.
So it's not just about the simulation itself, but the philosophy behind its creation and distribution. This aligns perfectly with the open source physics (OSP) project's goals.
Exactly. OSP aims to leverage open source tools to enhance physics education globally. The simulation is a prime example of this philosophy in action. The specific learning goals would likely include a solid understanding of vector resolution, the relationship between vectors and their components, sine and cosine functions, and the ability to apply this knowledge to solve problems.
The simulation is built using JavaScript and HTML5. How do these technologies contribute to the simulation's functionality and accessibility?
JavaScript provides the interactivity, allowing for real-time manipulation of the vector. HTML5 ensures broad compatibility across different browsers and devices. This combination makes the simulation accessible to a wide range of users, regardless of their operating system or device. The user interface is designed to be intuitive and user-friendly, minimizing the learning curve for students.
The intuitive design is key. A complex simulation with a clunky interface would defeat the purpose. The document mentions a study guide that accompanies the simulation. What does that include? The accompanying study guide includes a quiz and essay questions. How do these assessment tools contribute to the learning process?
The quiz reinforces key concepts, allowing students to self-assess their understanding. The essay questions encourage deeper reflection and application of the concepts. This combination of formative assessment tools helps students solidify their understanding and identify areas where they need further support.
It's a comprehensive approach to assessment, moving beyond simple memorization to deeper understanding and application. The guide also includes a glossary of key terms. Why is this important? The glossary of key terms is a valuable addition. It ensures that students have a clear understanding of the terminology used in the simulation and the broader field of physics.
Absolutely. Precise terminology is crucial in physics. The glossary helps to standardize understanding and avoid confusion. The document also suggests areas for improvement, such as adding more detailed learning goals and examples of how the simulation can be used in different pedagogical contexts.
That's insightful. Continuous improvement is essential for any educational resource. What are some of the other simulations available on the Open Source Physics Singapore website? The website offers a wide range of simulations covering various physics topics. This breadth of resources is a significant advantage for educators.
Indeed. The website provides simulations on mechanics, electromagnetism, waves, and modern physics. This comprehensive collection allows educators to create a more holistic and engaging learning experience for their students. The variety of simulations caters to different learning styles and preferences.
The sheer number of simulations available is impressive. It speaks to the commitment of the Open Educational Resources / Open Source Physics at Singapore project. What about the licensing and accessibility of these resources? The resources are licensed under a Creative Commons Attribution Share Alike 4.0 Singapore license. What does this mean for educators and students?
This license allows for free use, adaptation, and sharing of the resources, provided proper attribution is given. This promotes collaboration and allows educators to customize the materials to suit their specific needs and contexts. It's a powerful model for promoting open and accessible education.
The open licensing model is a key factor in the success of the OER initiative. It ensures that these valuable resources are widely available and adaptable. What are some of the limitations or challenges associated with using these simulations? While the simulations offer many advantages, there are likely some limitations. What are some of the challenges associated with using interactive simulations in physics education?
One challenge is ensuring that the simulations are used effectively within a broader pedagogical framework. Simulations should complement, not replace, other teaching methods. Another challenge is addressing potential technical issues such as browser compatibility or internet access. Finally, it's important to ensure that the simulations are aligned with the curriculum and learning objectives.
Effective integration into the curriculum is crucial. Simulations should enhance, not detract from, the overall learning experience. What are some best practices for using these simulations effectively in the classroom? How can educators maximize the benefits of these interactive simulations?
Educators should carefully select simulations that align with their learning objectives. They should integrate the simulations into a broader lesson plan, using them to introduce concepts, reinforce learning, or provide opportunities for exploration and discovery. It's also important to provide students with clear instructions and support, and to encourage active participation and discussion.
Active learning is key. Simulations should be used as tools to facilitate student engagement and understanding, not just as passive demonstrations. What are some potential future developments or improvements for this particular simulation? The document suggests several areas for improvement. What are some potential future enhancements for the vector component simulation?
Adding more advanced features, such as the ability to simulate vector addition and subtraction, would enhance its versatility. Incorporating more realistic scenarios and applications would also increase its relevance and engagement. Finally, developing more comprehensive assessment tools, such as interactive quizzes and problem-solving activities, would further strengthen its educational value.
Those are all excellent suggestions. The continuous development and refinement of these resources are crucial for maintaining their relevance and effectiveness. What are your overall thoughts on the impact of this simulation and similar OER resources on physics education? What is the potential impact of these simulations on physics education?
These simulations have the potential to revolutionize physics education by making it more accessible, engaging, and effective. By providing students with interactive tools to visualize and manipulate complex concepts, these simulations can significantly improve their understanding and appreciation of physics. The open-source nature of these resources also fosters collaboration and innovation within the educational community.
The potential for positive impact is significant. The accessibility and adaptability of these resources are key factors in their potential to transform physics education. What are some of the challenges in ensuring equitable access to these resources? Equitable access to technology and internet connectivity is a significant challenge in many parts of the world. How can we ensure that these valuable resources are available to all students regardless of their socioeconomic background or geographic location?
Addressing the digital divide is crucial. This requires collaborative efforts between educational institutions, governments, and technology providers to ensure that all students have access to the necessary technology and internet connectivity. Creative solutions, such as offline versions of the simulations or partnerships with community organizations, can also help to bridge the gap.
Collaboration is key. Ensuring equitable access requires a multifaceted approach that addresses both technological and socioeconomic barriers. Thank you for sharing your expertise on this important topic.
My pleasure.
The discussion has highlighted the significant potential of interactive simulations like this vector component model to enhance physics education. The open-source nature and accessibility of these resources are particularly noteworthy. The combination of 3D visualization, interactive elements, and accompanying study materials creates a powerful learning tool. The emphasis on OER and OSP principles underscores the commitment to making quality physics education available to all. The challenges of equitable access and effective integration into the curriculum remain important considerations for educators. However, the potential benefits of these simulations are undeniable. They offer a powerful way to engage students, improve their understanding of complex concepts, and foster a deeper appreciation for the field of physics. That was a great discussion.